Oh, it's in the
Yes, let's get started. So today and the 2 lecture next week, we're going to do the practice sessions for chapter 3 and chapter 4. Okay, and then we have a spring break. Okay, so the spring break will be the week of, let me see, the week of 15th, March 15th. Okay, and then the second homework will be due on March 23rd, I believe. Okay. So my plan for our first quiz will be on the 25th during class. So March 25th during class will be our first quiz. Okay. We'll talk more about that next week. Okay. So today is chapter 3 practice. Okay. So the first question on page 169, question number 2. Okay, so chapter 3 is propagation of error. Okay. The first question, we have 2 thermometers calibrated by measuring the freezing point of glacier acetate acid, okay, which is 16.6 degrees Celsius. Okay. So equal number of measurements are taken with each thermometer. And here is the results. Okay, the first thermometer is 16.4 plus minus 2 degree. The second thermometer is 16.8 plus minus 0.1 degree. Okay. So first part of the question, is it possible to tell which thermometer is more accurate? Okay. If so, say which one. If not, explains why. Okay. So in chapter 3, we talk about 2 similar things. Okay. One is precision, another one is accuracy. Okay. So precision, accuracy. Okay. So precision is judged by uncertainty. Uncertainty. And uncertainty is sigma, correct? And accuracy is calculated by the so-called bias. The bias is equal to the mean value mu minus the true value. So first part question asks, which thermometer is more accurate? So accuracy is judged by bias, so mean value minus true value. The true value is 16.6 degree, which is the freezing point of the glacier acetate acid. Okay. The mean value for the first one is 16.4. Okay. So the difference is minus 0.2. For the second one, the measurement is 16.8. Okay. Minus true value, 16.6. So it's positive 0.2. Okay. So they both differ from the true value by 0.2 degree. One is positive, one is negative. One is larger, the other one is smaller. So they are the same, they have the same accuracy. So we cannot tell which one is more accurate than the other. Okay, because they have 0.2 difference from the true value. Okay. And then part B. So part B is asked about the precision. Okay. So is it possible to tell which is more precise? Okay. So which one is more precise? The first one or the second one? The precision is judged by sigma, uncertainty. Where is the sigma? in the question is here. So plus minus 0.2 and plus minus 0.1 degree. So the smaller sigma is more precise. Okay, so the second thermometer has sigma of 0.1, so smaller than the first sigma for the first thermometer. So the second one is more precise because its uncertainty is smaller. Okay, so B, second, more precise. Okay, for part A is no, we cannot tell the difference about accuracy because both the two thermometer has the same accuracy. Okay. Any questions about the first question? Okay. So next, question number 4. Okay, so this one is relatively simple. For measuring processes, the uncertainty is approximately proportional to the value of the measurements. Okay. For example, a certain scale is said to have an uncertainty of plus or minus 2%. Okay. So that's 2% of the measured value. So object is weighed on its scale A, given that the reading is 100 gram, expressed uncertainty in this measurement in grams. Okay, so 2% of 100 gram, that's it. 100 gram times 2%, so that's 2 gram. So uncertainty for the measurement is 2 gram. It's part A. Part B, if it's 15 gram, what is the uncertainty? So same thing, for 15 gram times 2%, so that become 1 gram. 1 gram. Okay, so the uncertainty can be expressed as the measured value, like grams, or can be expressed as the percentage, like 1% or 2%. Okay. So that is question number 4. Next question is question number 6. So question number 6, the person get on and off a bathroom scale 4 times, okay, 4 measurements. The readings are 148, 151, 150, and 152. Okay. And each time after the person get off the scale, the reading is 2 pounds. Okay, so when he get off the scale, the reading should be 0 pounds, but the scale is shows 2 pounds. So that means the scale needs to be recalibrated. Okay. A, is it possible to estimate an certainty in this measurement? Okay. So uncertainty is judged by sigma. So the sigma of the whole population we don't know, okay, but we can calculate the standard deviation for the sample measurement, S. Okay, so and we have equation for that. So we can calculate the standard, the sample standard deviation S using this equation. Okay. So S is a function of sample size n is 4. We have 4 measurements. Xi, question gave us 144, 148, 151, 150 and 152. And then the mean value of the sample is, added together divided by 4. So we can calculate the S value. S is 1.71. Okay, so remember, S is called sample standard deviation, and sigma is called population standard deviation, which in our case is all possible measurement from the scale. Okay, sigma we do not know, but we can use sample standard deviation S to estimate sigma. Okay, so S is 1.71. So that is the uncertainty. Part B
I'm sorry.
about,
Could you? I'm looking at the equation, and I wrote it down, and I see that you wrote 4 there, but I'm not. I don't understand all the other operations that are in the root.
the 4 reading, he measured the weight 4 times. So that's 4 reading. So N is equal to 4.
Okay. And then, I mean, how did we get 1.71 though? Because the square root of 4 is 2.
Oh, I don't.
Right?
I don't give the details. You just
okay.
plug in a number into this equation, right? That's the sum of xi. Xi, for example, x1 is 148. X2 is 151.
Okay. I see.
Yeah. Okay. So that's something we learned from chapter 2. Part B, about the bias. Is it possible to estimate the bias? So the bias is the mean value, the difference between mean value and the true value. Okay. So when the people get off the scale, it shows 2 pounds or minus 2 pounds. It shows 2 pounds. Okay. But the true value after he get off the scale should be 0 pounds, right? So we can calculate the bias. So bias is mean value minus true value. Okay. So after he got off the scale, he measured 2 pounds, but the true value is 0 pounds. Okay. So the bias is 2 pounds. Okay. So what he need to do is he just recalibrated the scale. So when he get off the scale, it shows 0 pounds. Then after recalibration, we see the scale is unbiased. Okay. So that is question number 6. Next, 177, question number 2. So here, question number 2 here. A measurement of the diameter of the disk has uncertainty of 1.5 millimeter. How many measurements must be made so that diameter can be estimated with uncertainty of only 0.5 millimeter? Okay. So from chapter 3, we learned when we increase the number of measurements, the uncertainty will become smaller. Okay. So the equation for that is sigma of the mean measurement is equal to sigma over square root of n. Okay, so we use that equation, can be resolved that. So how many measurement is asked about n? Okay. So initially the sigma is 1.5 millimeter. And we want the new sigma of the average measurement is 0.5. Okay, so based on that, we can figure out how much is n. So n is 9. So when we have 9 or more measurement, then the uncertainty will become 0.5 or less. That is question number 2. Question number 4. All right, so this is about propagation of errors. So the volume of cone is given by this equation. So V is volume equal to pi r square h over 3. R is the radius of the base. So something like that. Okay. So R is the radius. So volume of the cone is a function of the radius, and h is the height. H is the height. Assume the radius is 5 centimeter. Okay, so radius is 5. Measured with negligible uncertainty. So sigma is 0 for R. For height, h is 6 plus minus 0.02 centimeter. Estimate the volume of the cone and find the uncertainty in this estimate. Okay. So the volume is a function of h and r. H has uncertainty of 0.02. R has no uncertainty, negligible. Okay. So the equation we're going to use for this is I'm going to show you later. First of all, V is pi r square h over 3. Okay. So we can plug in the number. R is 5, h is 6. So pi 5 square h 6 over 3, right? Okay. So first we calculate the V value. Right. And because R has no sigma, okay, so we only need to care about H. So we need to find the correlation between H and V. So again, based on that equation, we plug in R equal to 5, okay, and we leave H as that. Okay. So we found out V is equal to 26.18 H. Okay. Right. So based on linear correlation of error, a linear combination of errors, so sigma of Cx is equal to C is a constant, the absolute value of C times sigma x. Okay, so this is the equation we're gonna use. So here, V is 26.18 times H, and we know H has sigma of 0.02. We want to know the sigma of V. Okay, so sigma of V is equal to sigma of 26.18 times H. So 26.18 is constant. Okay, so that will become 26.18 sigma H. Okay, and the sigma H is given which is 0.02. So 0.52 cubic centimeter. All right. So that is question number 4. So this is the linear combination of sigma. So question number 6 is our next. This number 6 is here. A cylindrical hole is bored through a steel block, and the cylindrical piston is machined to fit into that hole. All right. The diameter of the hole is 20 plus minus 0.01 centimeter. Okay, let's draw something here first. Okay, so let's see, that's the hole. Okay, so that's diameter of the hole. Let's see, this x. So 20 plus minus 2.01. Okay. And then for the piston, which is inside the hole, that's here. Okay, this is the diameter of the piston. So let's say it's y. So 19.9 plus minus 0.02. And then the clearance is 1/2 the difference between the diameter. So the clearance is this. Okay, so that's the clearance. So yes, it is half of the difference between x, y. So half of the value of x minus y. Okay, so that's this question tells about that. So clearance is equal to 0.5x minus 0.5 y. Okay. So first of all, we can calculate the clearance by plugging in x and y. So x is 20, y is 19.9. Okay. So that's the clearance. Turned out to be 0.05 centimeter. And then let's figure out the sigma of the clearance. Okay, so which equation we're going to use? Okay, again, linear combination. So the equation we learned from chapter 3, one of them is the sigma of C1x1 plus C2x2 plus Cnxn, where C is are the constants, okay, is equal to this. Square root of C1 square x sigma x1 square
So in this problem, sigma represents the uncertainty.
Yeah, standard deviation. Yeah, uncertainty.
Standard deviation.
Yeah.
Uncertainty.
Yeah.
Okay.
Plus C2 square sigma x2 square blah blah plus say n square sigma x n square. So that's the square root of that. Okay. So and here is the constant. Okay. So the uncertainty for the clearance, which is 0.5x minus 0.5y. Okay. Based on this equation we just discussed, it's equal to C1 is 0.5 square. Okay. Sigma x is 0.01. Okay. Times 0.01 square. Okay. Plus C2. C2 here, you should pay attention, is minus 0.5. Okay. So minus 0.5 square. Sigma y is 0.02. 0.02 square. Okay. And also pay attention, this is plus. Okay. So do not use minus. Okay. From there, we can calculate the sigma of the clearance. Okay. So that is linear combination of measurements. So from section 3.2. Any questions so far? Okay. So question number 6.
The proper expression for that second part would be 0.5 plus or minus 0.01.
Correct. Correct. So the red expression, clearance is 0.05 plus minus 0.011 cm. So that's the clearance. See, you are right. Okay. Okay, and it's here. Next, 184. Seen as section 3.3. Okay. So that's the uncertainty for function of a measurement. Okay. 3.3. First, question number 4. So the velocity of sound in air at temperature T is given by this equation. Okay. So V is the velocity, T is the measurement of temperature in Kelvin, and V is in the unit of meter per second, M over S. Assume T has value of 300 plus minus 0.4 degree. So the uncertainty for temperature is 0.4. And asking us to estimate V and find the uncertainty for that estimate. So this is V is the function of T, the temperature. So we know the uncertainty for temperature, and then we need to calculate the uncertainty for V. Okay. So which equation we should use? So from chapter 3, section 3.3, if u is a function of x, and uncertainty of u will be du dx, the absolute value times sigma x. Okay, so in this problem, x is t, u is v, the velocity. Okay, so that's the equation we're going to use. So what we have here is temperature is 300 degree. Sigma t is given 2.4. Okay. First, estimate V based on the equation from the question. Okay. So plug in t is equal to 300. V is 347.1. Okay. So that is a meter per second. Okay. And then we're gonna calculate du dx. In this case, is dv dt, because v is a function of t. So dv dt, because v is 20.04 times square root of t. So that is 20.04 is times, okay, half. T is to the power of half minus 1. Okay, that's dv dt. Simplify that, it become this. So 10.02 times t to the power of negative 0.5. So the dv dt is estimated at the point of interest. The point of interest is when t is equal to what temperature? 300. Okay, so we plug in t equal to 300, we get dv dt. And then we can calculate sigma v. So sigma v based on this equation is equal to dv dt sigma t.
One sec.
Sorry.
I get that. Could you try it? There's nothing to read.
All right. Okay. So the absolute value of dv dt times sigma t. Okay. So that is 0.5785 times sigma t. Sigma t is given 0.4. 2.4. So sigma v is equal to this much. So we can express v is 347.1 plus minus 0.23 meter per second. Okay. So that's the uncertainty for function of one measurement. Okay. So here, V is a function of temperature T. All right. That is question number 4 here. Next, question number 6. So question number 6, is similar. Similar. So the change in temperature of iron bar brought about by transfer of heat is given by this equation. So delta T is equal to delta Q over MC. Delta Q is the amount of heat being transferred. M is the mass of the bar. C is the constant. It's called the specific heat of iron. Okay. C tells us as
Isn't Q like a isn't this like a chemistry problem?
this is the physics problems.
Oh, physics. Okay.
Transfer of heat. Okay. So delta Q is 1210 joules, unknown with negligible uncertainty. So that's good. So delta Q has no uncertainty. The mass has uncertainty. So 0.54 plus minus 0.01. So the uncertainty for the mass is 0.01 kilogram. Estimate delta T and find uncertainty for the estimate. Okay, so basically the same question. So here, delta T is a function of mass. And we know the uncertainty for the mass, and we want to know the uncertainty for delta T. Okay. We use the same equation. So first, let's calculate delta T. Okay. Is equal to delta Q over MC. Okay. So plug in the number, delta Q. MC is, M is 0.454. C is 448. Okay, so this part is easy. Then we need to calculate uncertainty. Okay, so here the function is delta T. So d delta T, the x is n, the mass. So d delta T dn is what we are interested in. Okay, so that is equal to d delta T is equal to delta Q over C times Im to the power of -1. Yeah. Okay. Which is simplified as this. -2. Again, we plug in the value of delta Q, C, and M, which are given from the equation. Delta Q is 1210, C is 448, M is 54.54. Okay, so d delta T dm is equal to minus 9.2623. Okay, so based on the equation, d sigma delta T, the absolute value, d delta T dm times sigma n. Okay, so that is positive 9.2623. Sigma m given, sigma m is 0.01. So that will become 0.093 degree Celsius. So we can express delta T as 5.0017 here, plus minus 0.093 degree Celsius. All right, so the question number 6 is pretty much similar to question number 4. So we have one measurement. Then we want to find the uncertainty for the function of that measurement. Okay.
Professor, I know this is probably elementary or something like that, but I can see how the joules are canceled out, and we only end up with the degrees Celsius. But how does the kilograms get canceled out?
You don't need to worry about that part. Okay. So
okay.
Yeah. So the unit is you don't need to worry about unit. As long as the number is okay, that's fine. Okay. So
okay.
That is physics problem. Okay. So yeah.
Okay.
Okay.
I saw how the joules got canceled, but I wasn't seeing how the kilograms did. That's all.
Okay. All right. Let's finish the last question for chapter 3, and that's called a day. So question number 9. So the density of a rock will be measured by placing it into a graduated cylinder partially filled with water. Okay. Yeah, we do similar experiment in CE305 where we measure the specific gravity of sand and aggregate in concrete. Okay. Yeah, if you take 375, which means next semester we're gonna do that similar experiments. Anyhow, so then we measure the volume of water displaced. So the density D is given by this equation. So D density is equal to M, which is the mass of the rock, over V1 minus V0. So V0 is initial volume of the water, and V1 is the volume of the water plus rock. So basically we do something like this. So that cylinder, we have some water, and then we put a rock. Okay. Into the water, and the water level become higher. Okay. So the volume, the V1 is the V0 is the initial volume, and the V1 is the volume of the water plus rock. Okay. Assume the mass of the rock is 750 grams with no uncertainty, but V0 has uncertainty of 0.1, and V1 has uncertainty of 0.1 also. ml is milliliter. Okay. So estimate density of the rock and find uncertainty for that estimate. Okay. Or so let's call V is the volume of the rock. So V rock is equal to V1 minus V0. Okay, so the new volume V1 minus old volume V0. Okay, so that's the volume of rock. So that is equal to this, based on the question, equal to okay. And then let's find out the sigma of the volume of rock. sigma V rock is equal to sigma of V1 minus V0. Okay. And how to find that? That is the linear combination of measurement of error. The equation is here. Okay, C1x1 plus C2x2 plus Cnx1 is equal to C1 squared times sigma x1 squared, blah, blah. So using that equation, okay. Because the constant is 1, so it just equal to sigma V1 squared plus sigma V0 squared. Because the constant is 1, so the 1 squared, right? 1 squared. So sigma V1 is 0.1. Sigma V0 is also 0.1. So sigma V rock is this much. Okay. And then let's calculate dd. D is the density dV. Okay. So D is equal to m over V1 minus V0. Okay. And V1 minus V0 is defined by us as V rock. So D is equal to m mass of the rock over volume of the rock. Okay. So dd over d rock, okay, is equal to d m v rock. So this is minus 1 to the power of negative 1 d v rock. Okay. So that is minus 1 times m v rock to the power of negative 2. Okay. And m is 750. Okay. And v rock is 313.2. Okay. So dd over d rock will become minus 0.007646. Okay. So finally, sigma d is equal to absolute value of dd dv rock over d sigma v rock. Okay. So that equation is based on propagation of error, this equation. Okay. So the first part is this 0.007646. And sigma v rock is also calculated here, 0.1414. So it turns out sigma d is 0.0011. So we can express d finally as where is d? We haven't calculated d yet. Okay. So the d is equal to m v1 minus v0.
2.394.
Yeah, 2.3946. Okay. For 6. So D is equal to 2.3946 plus minus, yes, okay, plus minus 0.0011. Unit gram per milliliter. All right, so that's our practice set questions for chapter 3. So we learned propagation of error. Okay, so what's the difference between accuracy and precision, and the linear combination of propagation of error, and also the function of uncertainty for function of measurements. Okay. Next 2 class, we're gonna do similar things, questions for chapter 4. Okay, so before the spring break. Okay. All right. Any questions for today?